Textbook game theory usually employs a 2x2 payoff matrix to explain game theory. But these matrices are difficult to follow, and their format unnecessarily restricts the kind of binary choice games that can be explained. For example, a typical payoff matrix for a PD game may look like this, where the number represents cardinal payoff indexes, with high numbers indicating higher payoffs, and L represents the left choice, and R represents the right choice. But the meaning of this payoff matrix is more apparent if we extend it to a multi-party situation of n persons. The number of persons choosing R increases from left to right, and the number of persons choosing L increases from right to left. The payoffs for choosing R increases as more people choose R, and the payoff for choosing L decreases as more people choose L. The endpoints of these payoff curves represents the cardinal payoff indexes. The payoff curves assume that each of the person making the same choice has the same average payoffs. Plotted this way, it is very clear that choosing L is the dominant strategy. It is also very easy to plot the collective payoff curve over the distribution of n people over choice L and choice R. The collective payoff is simply the payoff for L weighted by the percentage of people choosing L, plus the payoff for R weighted by the percentage of people choosing R. This collective payoff curve clearly shows that everybody choosing R at A is collectively superior. But because L is the dominant strategy, everybody ends up choosing L at B. This is, of course, the classic prisoner's dilemma game. The advantage of the multi-party format to analyze binary choice games is even more compelling when the payoff curves intersect each other.
In some game situations, there could be a double reversal of payoff dominance, when the payoff of one option increases at a decreasing rate. Suppose the payoff for R is such a curve, with the payoff for L falling. The payoff curve of R intersects the payoff curve of L twice, so L dominates R until a critical mass is reached. After that, the mutual positive externality of choosing R attracts more people for that option. And when most people are choosing R, some individual might gain by not choosing R. This double reversal of payoff dominance produces two stable equilibria. The superior equilibrium occurs near the right end at A, and the inferior equilibrium occurs at the extreme left end at B. The network effect of many communication systems comes to mind. When few people own fax machines, their usefulness is limited. As more and more people own fax machines, they become very useful, and it pays to own one too. But when most people have fax machines, some people can free ride on those who own the machines. In the case of birth gender distribution, the objective payoff is higher when the gender ratio is about half and half, regardless of one's preference for boys or girls. Suppose R represents the preference for boys. The payoff curve might look like an inverted U. And the same for the L payoff curve for girls. But if there is a universal preference for R, say boys, the payoff for R will dominate the payoff for L. If parents can freely choose the gender of their babies, all babies will be boys, since having girls is everywhere inferior to having boys. The collective payoff curve shows that an all-boys solution at B is stable. But the all-boys solution, though stable, is inferior to a more mixed gender ratio at A. But if the preference for boys depends on the scarcity of girls, and vice versa, then the payoff curves would reverse their dominance, where the gender ratio is about half and half. Here, the stable solution at A is also collectively superior.